Thank you very much for attending this IAS testing lecture today. So today we have a very special guest from the Script Research, Professor Phil BARAN. And since this is his first time to come to Hong Kong, we are very lucky to have a Professor BARAN at the HKUST. So to begin with his lecture, let me briefly introduce his background and career. So Professor BARAN earned his bachelor degree in 1997 from New York University, and PhD in 2001 from the Script Research Institute under the guidance of Professor Casey Nicolau. And then right after his PhD study, he served as a postdoctoral associate at Harvard University from 2001 to 2003. And then subsequently, he joined the faculty at the Script Research Institute, and he started his independent career. And then he's very young and talented chemist. And when he started his independent career, he was only 26 years old. And before he became an independent career, he published 42 papers during bachelor and PhD and postdoc. So very productive and amazingly young chemist. And his research mainly focused on organic synthesis, and he covered many different fields. For example, total synthesis of complex natural product and methodology and medicinal chemistry and peptide chemistry. And nowadays, he mainly focuses on the electrochemistry, which can be simplified in organic synthesis. So please join me to warm welcome to Professor Phil BARAN.
Well, thank you so much, Yu, for this very flattering introduction. It's great to be in Hong Kong. And today I've been told I have like 90 minutes, but I won't go the full 90 minutes. I'll try to keep all of you awake and entertained. The laboratory has focused over the past 2 decades on something that's very, very simple. We're just aiming for the ideal synthesis. So when I was a kid, people told me that the ideal synthesis involved mixing all your chemicals in a bathtub by a blind person with one arm, and the yield is 100%. The problem with that definition of an ideal synthesis is it has no educational value whatsoever. So I can't tell a student to make Taxol in one step in a bathtub and expect them to be successful. But what I can do is give them this equation for ideality, which says basically the only thing you should be doing is making skeletal bonds. Carbon-oxygen, carbon-nitrogen, carbon-carbon, and nothing else is worth your time. Everything else is what we call a concession step. So today, I'm going to guide you through a journey that started with natural product chemistry that led us to the area over a decade ago of electrochemistry, and show you how, hopefully in a convincing way, when strategically applied, electrochemistry can lead you to more ideal syntheses. Now, as a bit of a historical background, when I started my career, of course, we were guided by the Bible, shown here, written by E.J. Corey on how to do retrosynthetic analysis. And the problem with this area, which I call like the age of feasibility, when I grew up, people just cared about making compounds any way you could make them. It didn't matter how many steps, just to show you could make them. With enough money and time, you could make anything you wanted. And so a lot of these glorious natural products you see here were made in really long-winded routes. And when I taught classes in this area, the students would write proposals that were extraordinarily boring. I would fall asleep grading the papers because it was impossible to be excited by the proposals they had, because they were using known rules to put together molecules in a boring fashion. So almost 20 years ago, we put forward, in this paper in 2007, a set of 10 rules that a student could easily follow to approach ideality and make a molecule in as minimum number of steps possible. Now, one of these on the slide here, Taxol, of course, Professor Nakamura worked on. That was an incredible time together. Whoever's working for you is a very, very lucky student or postdoc. He's one of the most incredible and talented people I've ever worked with. So thank you, Yu, for this great invitation. So the great thing about ideality, pursuing ideality, is it places you in the role of becoming an inventor. Because a student that puts together a proposal trying to make an ideal synthesis, they often have a retrosynthetic disconnection for which there is no reagent. They put a question mark over the arrow, and they say, I don't know how to do that. But it makes you invent something that will enable you to do it. Now, you don't need to make a terpene or an alkaloid or a peptide and apply ideality. You can do things like oligonucleotide synthesis as well. I could talk to you for an hour about oligonucleotide synthesis and how we tried to apply the principles of ideality to one of the most important biopolymers on the planet. Similarly, pursuing natural products with an eye towards ideality turns you into an inventor. So our work on palaomine, I don't know, more than 15 years ago, led us down the road of radical retrosynthesis that I'll talk a lot about today. And our work on this marine natural product, dixamycin, led us down the road of electrochemistry that I'll focus completely on today. If you're interested in why we pick a natural product, half the lab still does natural product synthesis, why we pick them, what we learn during this process. We wrote a review about it that summarizes, 20 different total syntheses over the past few years. You can read in that accounts paper the reasons why we pick natural products and what we learn from them. And here's a recent example that was published about a year ago, this interesting marine natural product, portamine, with amazing bioactivity that we can now make on gram scale, was spearheaded by this very talented student, Jun Chen, who's now a postdoc in Chris Parker's group. But collaborating within Scripps, we were able to find out the mode of action of this very interesting compound. And so endeavors like this in our lab are still the bread and butter of what we do. It's the foundation of what we do in our laboratory. So I'm going to dive deep and focus on one thing today. And my favorite reaction of all time is what I'll start off with, the Kolbe synthesis. Does anybody teach this reaction in class? Do any of you learn it in undergraduate chemistry? Some of you say, yeah, but I don't know anybody that really learns this reaction in undergraduate chemistry. It's usually in the end of the book. They teach it as like a random, crazy curiosity. It's one of the most useful reactions on paper, which I've never seen anybody until very recently actually employ. Now imagine, put yourself back into the mindset of an undergraduate chemist who just walked into the class for the first time in Orgo 101, and your teacher tells you that the reaction in the box at the top works. My question to you is, would you ever do a Wittig hydrogenation or a Wurtz coupling ever again to make a carbon-carbon saturated bond? On the quizzes in the midterm and the final, you would use this reaction to make everything. Yet it doesn't exist. And if you go into the sort of encompassing libraries of what people do in medchem, you look at the data, nobody uses the Kolbe. It was discovered back in 1834. Faraday was electrolyzing vinegar, and he found he made some bubbles. And then 10 years later, Kolbe said, hey, dude, those bubbles you're making, that's ethane gas. And now we call it the Kolbe electrolysis. But fast forward over 100 years, nobody uses this reaction. And the question is, why? Well, there are some sporadic applications, but the applications of the Kolbe are relegated to substrates that have no functional groups that can be oxidized, because this is a very harsh reaction. In fact, the Kolbe reaction uses an extreme overpotential with platinum electrodes. It's kind of like taking your molecule and putting it into the electric chair. You buzz the crap out of it until nothing remains. And so what I'll show you later is an example where you can take octanoic acid using Kolbe, and you can dimerize octanoic acid. But if I take octenoic acid, one olefin at the end, what do you think the yield is? It's 0%. So there's no functional group tolerance in this reaction. So we wondered, would it be possible to take the Kolbe reaction, instead of making it strongly oxidative, make it mildly reductive by using these now very popular, what we call redox active esters. Now, redox active esters are nothing more than peptide bond coupling agents. They were used by Sheehan in the 60s to make penicillin. And redox active esters, just like amide bond coupling agents, you can add an amine to make an amide, but you can also add an electron. When you add an electron into an NHPI ester or a redox active ester, you self-immolate it. You inject an electron, you lose CO2, and you liberate a radical. And we wondered, could you take two different radicals from two different organic carboxylic acids and get them to heterocouple? That was the idea. We had this reaction on paper for years. Nobody wanted to work on it because they said, hey, Phil, that's never going to work. So we had one postdoc who was naive enough to work on this project. And his naivete landed him a job at SIOC, where he's now a professor. And he found that by optimizing the conditions, most notably the ligand employed, a tridentate ligand is key to capture the alkyl radical and generate the heterocoupled product. So as you see here, really a simple screen of activating agent, a simple copper diamide, simple electrodes, a simple solvent, but the ligand is key to get this reaction to work. Well, with this reaction in hand, we knew we had something very special. And we went about to see if it worked under any other conditions. So we tried chemical conditions, chemical reducing agents, photochemical means, and nothing worked We wanted to make sure that this is actually something you need electrochemistry to do. And it turns out electrochemistry is key. And we collaborated with Martins here, who works at Bristol Myers Squibb, and he screened dozens of different things photochemically and didn't find anything that gave anything other than the homocoupled product. The scope of this reaction is really broad. So you'll notice here the functional group tolerance is very high. It's very mild, so it doesn't epimerize centers that are amenable to epimerization. It can be used to make primary-primary couplings work, primary-secondary, secondary-secondary. I'll show a lot of examples today of quaternary centers that can be forged with this technique. And all the compounds I'm showing you here have been made before. It's really easy to go to SciFinder and find organic molecules that you could use this technique, because all you need to do is repurpose 2 known carboxylic acids and put them together to get your product. You can also do these academic tricks where you make these, in this case, these are beetle pheromones. Now, if I was a beetle looking to attract the opposite sex, I could either make this compound in my own body, or if I had access to a potentiostat, I could do it a lot quicker with this chemistry. So you can just take a desymmetrized ester, you can do cross-coupling number 1 and then 2, or reverse the order and get either an enantiomer of your desired pheromone to attract a partner. And Yang, who is now a professor in China, figured out this chemistry. Now, the procedure for this reaction is ridiculously simple. It's my favorite part of all the chemistry I'm going to show you today. It can be done by a 5-year-old, or maybe a primate that's properly trained in the zoo can run this reaction. If you know how to make an amide bond, you can do this reaction. You mix the reagents together. Don't add the amine or you'll make an amide. Add the nickel catalyst, press the button on the potentiostat, and you get out your product. It's that simple. Here's an example where I told the team, look, let's do this under the most simple conditions you can imagine, with the worst technical grade of all reagents. The solvent was not dry. There's no degassing. We didn't even use a fume hood. We simply wrapped the device in a Ziploc bag on a gram scale. And as you see here, it worked just fine. Even the nickel catalyst was not very good, but it worked just fine. Mechanistically, what's going on? Well, we could talk for another 30 minutes about the mechanism of this reaction. It's remarkable that it gives you the heterocoupled product at all to begin with. And on a broad stroke, I can tell you what's going on mechanistically is that a few things are getting reduced. So the nickel catalyst is getting reduced to nickel 1. There's probably some nickel 0 in there as well. The redox active ester is getting reduced at the cathode. That generates the radical, which is then captured by the nickel. And by virtue of the right ligand employed, you get the desired heterocoupling product to result as the main product. Now, you may have noted that one of the components is used in 3 equivalents, and one of the components is used in 1 equivalent. But just like olefin cross-metathesis, if you have one component that does not like to dimerize, you can get away with 1 to 1.5. So here are examples of molecules that can be made with a near stoichiometric amount of coupling partners to generate useful carbon-carbon bonds. Now note, despite that this is a reductive reaction, it tolerates things like alkyl and aryl aldehydes, which are super amenable to reduction. You can use this to make a whole variety of compounds and, again, simplify the way these molecules are made in a rather dramatic fashion. Now, as a molecule maker, this is what appeals to me most, and emphasizing to you that there are really only 3 ways of making carbon skeletons in organic chemistry. And you may say, Phil, that's ridiculous. I know 100 ways of making carbon-carbon bonds. But I'm talking about at a 50,000-foot view. And I'm going to summarize 150,000 publications for you in 3 slides. The first way of making carbon-carbon saturated bonds is by making unsaturated bonds and then reducing. That means Sonegashira reduction, Heck reduction, Suzuki reduction, Aldol reduction, Wittig reduction. Here's an example of that. This JMedChem paper, they took a steroid. They took 7 steps to make 1 carbon-carbon bond. In terms of ideality, the ideality is very low because there's only 1 step that does anything. The rest of the steps are a complete waste of your time. Now, if you're an undergraduate, you may like these steps because the TLCs look good, the columns are fun to run, and after a week of work, you feel like, wow, I got a lot of stuff done. But in fact, you were kind of like a hamster on a wheel doing nothing. Alternatively, you start off with a commercially available steroid and just do one coupling, and you're done. You don't need to protect the alcohols in the steroid because 1-electron chemistry doesn't care about your 2-electron problems. You often don't need protecting groups in radical chemistry. The second way of making carbon-carbon bonds is by directly making them. That can be a Wurtz coupling, or it could be a boron-alkyl-Suzuki reaction, or it maybe is a Wurtz coupling, or just a simple enolate alkylation. And here's an example of that. These folks in this medchem group took 7 steps to make this simple amino acid. And you look at the steps yourself. Do you want to do any of these? I personally don't want to do any of these steps. Protecting group manipulations, redox fluctuations, chiral auxiliaries, enolate chemistry. Nobody wants to do it. Now, the practitioners in this work are not stupid. They're just using whatever the methods they have available to them. Alternatively, I can just take glutamic acid, which is free, that keto acid, which is nearly free, dump them together, have an espresso, and when I get back to the lab, the reaction is done. Whatever EE of amino acid I start with is what I get out. So in this case, we started with pure glutamic acid, 99% EE, and the product we got was 99% EE of the product. So you decide, which one would you rather do? 7 steps of misery or 1 step of fun? The third way of making carbon-carbon bonds is the funniest way. This way doesn't make any carbon-carbon bonds at all. It's the Christmas tree model. So you buy a Christmas tree and you decorate it. So here's an example of that. These folks in this pharma company needed this amino acid you see here. And in order to make it, they went to the computer and they said, hey, I found this pyridine containing a cinnamate group. It has all the carbons I need to make the amino acid. All I need to do is some redox pounding to get it to be correct and fashion the chiral center through a chiral auxiliary, and I get out the desired product. And you see here a litany of steps of misery for what? Alternatively, I start off with pipacolic acid, aspartic acid, and I go have my cup of coffee, and when I get back, I get the exact same product. Any protecting group you want, and both of these materials are nearly free. So you decide, what would you rather do? Now you may say, Phil, it's not our fault. This is the way we've been trained. In fact, you're right. From the time you were a baby, your parents taught you about opposites attract. You played with magnets, and the North and the South Pole attracted each other. And when you got to undergraduate and graduate school, they taught you about retrosynthetic analysis, and they said, you make disconnections using polar-guided rationale, where you take a functional group and you say that's delta plus, this is delta minus, you cut between the plus and the minus, and that's how you get your bond. You remember? That's how everybody learns retrosynthetic analysis. The problem with this way of learning retrosynthetic analysis is that it ties you to a little annoying thing called the protecting group industrial complex. And the choreography of the steps you need to use make normal synthesis really long and laborious. How about a computer? Can a computer help you? The problem is the computers are all programmed with the same flawed logic. Now, I'm not saying you need to stop teaching polar bond analysis, but if it's the only thing a student knows, they're going to be intellectually handicapped. And that gets me to a point that we tell our families. Like, who tells their family when they do synthesis, oh, Mom, how do I explain it to you? It's like Legos. It's molecule making is like putting together Legos. Does anybody use that analogy? I use it. It's lying. Because if organic synthesis was like Legos, that company would have been out of business a long time ago. As all of you know, organic synthesis doesn't work. Often everything fails. And so making molecules is actually pretty difficult. If I told a 10-year-old child to make compound 1, and I gave them a box of building blocks that were all carboxylic acids, they would say, hey, Phil, I found a square, and I found a hexagon. Can I put them together? And they would be right. So radical retrosynthesis divorces your logic from polar bond disconnection, and as a result, you identify the most convergent disconnection, you do it convergently, you put them together, and you get out the desired product in a fraction of the number of steps. In this first disclosure, we eliminated more than 160 steps from the way these molecules were made, which is, I think, a pretty radical, pun intended, advance. Now, the analogy can be made to cross-metathesis. You know, the late, great Bob Grubbs, one of my favorite papers from him is this one. You probably have all studied it in graduate class. And in that work, you can take 2 different olefins, you can couple them together, and in its wake, lose ethylene gas. And the analogy holds true here. For doubly decarboxylative coupling, you take 2 acids, you put them together, lose CO2, and you get your new carbon-carbon bond. Okay, so let's move to total synthesis. We've been obsessed with progesterone as a community for eons. In fact, the beginning of organic chemistry was looking at steroids like this. People like the late, great Stork and Eschemoser, Van Tammelen, even Sharpless worked on this, Corey, Johnson. They all worked on this problem. And if you give it to a student has no problem saying, oh, I know how to make this with cation olefin cyclization. That's how nature makes it, right? But if you tell the student, make that polyolefin as one geometrical isomer. It's actually pretty hard. In fact, when I teach this in class, it's impossible to understand. So Steve and Max, really talented graduate students, became obsessed with this problem and wondered, why is it that it's so difficult to make these compounds? If I were to tell you none of you can leave this room until you tell me how the 5 building blocks on the right are stitched together to the compound in the middle, I think many of you would be here for a long time. I know I would be, because I haven't memorized it recently. I have to memorize it before I teach class, because it makes no sense. And organic synthesis shouldn't be like that. Now, meanwhile, the late, great Negishi taught us that we can make olefins without making olefins by instead disconnecting the bond adjacent to the olefin using a cross-coupling. And nature has been making terpenes for 1 billion years in the same way we generate an automobile, through an assembly line approach. So we thought, what if we could put these two together? What if we could take vinyl halo acids and piece them together one at a time in a way that's super intuitive and easy to understand? And we did that electrocatalytically. This was done during COVID, and what we found during that period was the way to get this electrocatalytic reductive coupling to work was by adding 30 mol% of silver nitrate. Without the silver nitrate, the chemistry, none of it worked. And I'll explain to you mechanistically what's going on in a moment. We applied this transform to more than 14 different natural products, as I'll show you in the next slide. It tolerates free alcohols, free carboxylic acids, beta-ketoesters, skip-dienes, alkynes. Secondary acids work just fine. You can use this on aldehydes. You can do it with furans, epoxides. It tolerates all sorts of functionality that are super sensitive and normally wouldn't be amenable to a reductive cross-coupling. You can take these interesting intermediates, mix and match them, and make any one of these very interesting smelling natural products. They're perfumery ingredients shown here. We even showed how you could revitalize the synthesis of vitamin D by using this disconnection twice. Both of the blue bonds in that structure were made using this nickel electrocatalytic silver-assisted chemistry. What's going on? Well, when you add silver nitrate to this reaction, a spontaneous deposition of silver nanoparticles takes place on the surface of the cathode. And that serves to really do one thing, and one thing really well. It attenuates the reactivity of the cathode, so you do not get premature reduction of the nickel, and you don't get premature reduction of the redox active ester. And that's what facilitates all of this chemoselective cross-coupling chemistry. If you're interested in learning more about the mechanism of this, you can scan that QR code. It will take you to a YouTube channel where we talk for 30 minutes about the mechanism of this reaction, which was a lot of work to figure out, involved a lot of material science, surface chemistry, kinetics, labeling, and finally we figured out what was going on here. But if you're curious, you can check out that video. All right, so if I go to a company and I tell them about terpenes, they start yawning and falling asleep. We don't care about terpenes, Phil. We care about things like that. Homotyrosine is currently $1,200 a gram. Why? It's a simple compound. Well, the answer is the way it's been made to this point has all been with polar bond disconnection. So all of the ways of making these compounds are miserable. You might say, oh, Phil, I'll use the Suzuki coupling. Go ahead. Right there is Suzuki coupling. You're going to take 10 steps to do it, and only one of those steps makes a carbon-carbon bond. It's miserable. Now, if I went back to the 10-year-old kid and I said, hey, I need your help again. How do I make this molecule? The child would say, well, there's a hexagon and there's a chain. Can I just put those two together? And that would require that we take glutamic acid and couple it with iodophenol, which is crazy. But if you could do it, it would be the most direct way of making this molecule because both of those ingredients are free. Now, we tried every decarboxylative coupling that we could find, the ones we had worked on back in 2015, the photochemical, the electrochemical, everything. We tried them all, and none of them worked. If you're interested in all the ways of doing decarboxylative coupling, we wrote a review about this. So there's the canonical couplings of the Kumada, Negishi, Suzuki type. There's the oxidative regime. There's the reductive regime. None of them worked. And we went to companies. We collaborated with 6 different pharmaceutical companies in this project. And we said, hey, folks, do you like decarboxylative coupling? And they said, oh, yes, Phil, we like it. It just doesn't work when we need it to. I was like, what do you mean? That's really sad to hear. And they explained to me, well, Phil, you don't understand. We do things with a lot of heterocycles, free OHs, NHs, and those destroy the reaction. When we try strange redox active esters, those also don't work very well. And a quote that they told me stuck with me forever, and maybe it will change the way you do chemistry as well. They said, Phil, what you don't understand is medicinal chemists want a reaction that works in 10% yield on 90% of the substrates. And what you keep publishing in JACS are reactions that work in 90% yield on 10% of the substrates. I said, oh, that's a pretty good point. It's a good critique. So can you give us a list of all the reactions that do not work? And that will be the substrate scope for this paper. So we got 100 examples from all these companies, and we went to work. We reasoned that maybe the silver chemistry I just showed you would endow this reaction with enough chemoselectivity to make it work. And so a team was put together. Max, who's now at BMS, Gabriele, who's now at the University of Graz, Jin is at a company, biotech in San Diego, and Tamara is our lab manager, and Simon, who's pursuing a postdoc at MIT. And what we did was we compared this electrochemical silver-assisted reductive coupling with all the other methods that are out there. Martin came to the rescue again from BMS, and what I'm going to show you are all the comparisons. As the substrates crawl across the screen, what I think is most remarkable is the binary level result, where often this is the only reaction that works for these people who are trying to make these molecules, and the decarboxyl coupling doesn't work in any other way. This is an extremely enabling reaction that has now been used by at least a dozen companies I'm aware of. You can even find it in some patents. Despite it only being published in 2022, you already find it in the patent literature. I would advocate that it's probably the most robust way of making an aryl-alkyl linkage that currently exists. Here's an example from a company where they were trying to bring this compound in the middle for cancer. They were trying to make it. They couldn't make it. They tried everything. They even tried Suzuki on the vinyl triflate, and when they tried reduction of the olefin, it aromatized, so they couldn't even use 2-electron chemistry. We did it on the first shot, 41% yield. They subsequently have gone on to make libraries of these compounds using this chemistry, and one of them went all the way to process chemistry. Now, procedurally, I have run this reaction myself, and I have to tell you, the hardest part of running this reaction was weighing out the starting material. So it's an extremely easy reaction to run. It's very difficult to screw it up. Everything is open to the air. You don't need to purify anything, even your catalyst. You're definitely not your starting materials. You just dump it, stir it for a couple hours, and it is done. Can you do it in parallel? Yes, you can run 24 of these at a time if you want. So Biogen did 24 examples that were not in the paper, just randomly chose them from the collection. Of those 24, 19 of them worked. You could then scale those up on the carousel. Out of those 6 that they scaled up, 5 of them worked. 1 of them was unstable. That indole, apparently a cyclopropane, opened up upon standing. If you have a redox active ester that is unstable, you don't need to isolate it. So all of these compounds were made by doing an in situ preparation of the redox active ester as shown here. And you can, in fact, scale these reactions up very easily. The cost of the equipment in the box is roughly $150, $200. And after you buy the equipment, just a simple peristaltic pump and a couple of Teflon enclosures for the electrodes, you can keep reusing it over and over again. And now the cost of something like homotyrosine is negligible. In fact, when we published this paper, we gave out homotyrosine for free over Twitter. If you need some, just email me. I'll send it to you. You can make quaternary centers with this as well by simply adding a little bit of binap and pyridine to this reaction. Now quaternary center formation to make aryl-alkyl linkages becomes a reality. And comparing it to the state of the art, this again appears to be the best way to make such compounds. And it's a kind of game changer for medicinal chemists. Because if you look at the patent literature, these 4 compounds have been made using some of the worst that organic synthesis has to offer to society. Take a look. All of these molecules are made by looking at the quaternary center as being the main focus of the retrosynthetic analysis. And now you can just buy 2 commercial materials, dump and stir them together, and get the exact same product without doing all this 2-electron, mostly enolate chemistry to make such compounds. You can also do this in unpublished work to make gem diarylated structures. These are really hot in the medicinal chemistry literature. They're really difficult to make, as you can imagine. Now you can take a bromo acid, do cross-coupling number 1, then cross-coupling number 2, and now you have a gem diarylated quaternary center. This was done in collaboration with many different companies. All of them are using it. Let me show you an example of how this can really benefit someone who's practicing medicinal chemistry. These are known compounds in the patent literature that people had to make before. Take a look at this example, this first one. Everything is 2-electron chemistry, of course. Friedel-Crafts, pyrophoric reagents. It's miserable. Nobody wants to do this. And what if you're not using an indole that doesn't do a Friedel-Crafts? What if you have something else? Here, you just take a bromo acid, which is commercial, cross-couple number 1, cross-couple number 2, done. Here's another example. Look at this misery. This oxetane, of course, needed to be formed from a malonate, reduction, and then some sort of cyclization, which proceeded in really low yield. So over 4 steps, they get 0.1% yield, which is enough for a medicinal chemist, but not very convenient. Alternatively, you just take a bromo-oxetane, cross-couple 1, cross-couple 2, done. Here's a third example. Misery. Condensation chemistry, it takes a couple of steps to make that, and you end up with one isomer. The pyridine is at the C2 position, or the quinoline, C2 position. But what if you need the C3? You can't use this chemistry to make the C3 analog. Now you can. Just dump and stir 1, do it again, and you get now the constitutional isomer with the nitrogen that's not adjacent to the cyclopropane, which if you're making analogs could be really, really interesting, but completely inaccessible with the 2-electron chemistry. So let's go to 1, 2, 1, 3 functionalized motifs. These are normally made through aldol chemistry, monic chemistry, dihydroxylation, dipolar cycloaddition. These are the general ways that you're taught in undergraduate how to make these structures. And they're all polar bond disconnections. Everybody has probably spent a lot of time in grad school memorizing Falcon-On, transition states, Newman projections to figure out how a Grignard adds to a carbonyl. I see people laughing. You know, right? This happened to you, right? It's miserable. Nobody wants to learn this stuff, but you need to learn it. Alternatively, what if you could just take acids with an alpha heteroatom and just couple them together and make diols, amino alcohols, aldol products, monic products without anything? You don't need to know anything about stereochemistry. What if you could do that? Well, we tried, and unfortunately it didn't work with the original doubly decarboxylative conditions, but when we added silver to this reaction, it worked really well. And here are some very simple examples. If you were to teach in one of the graduate classes, ask the question to the students, how do you make these molecules? Disconnect the bond, which is strategic to break. Anybody who would break the blue bond would fail the class. It makes no sense, but now it does. It's actually a very easy way to make these compounds. And this can be used to dramatically simplify the way you do chemistry. Here's an example. This compound took 7 steps to make. It's a trivial looking compound. Why is it taking so long to make this compound? Now you can just make it from a glutamate and glycine, and you're done. This compound, interesting little sugar molecule, took 6 steps to make. Why? So long. Now you just make it in 1 step, 2 commercial available materials, dump and stir them together, and you're done. You can take Lipitor, side chain. You know Lipitor, probably your parents are on it, statin medication to lower cholesterol. Because of the success of the statins, that building block in the middle is nearly free. And that building block is like an aldol cassette. And with a ligand, you get only the cis product. And without the ligand, you get only the trans. Why? Well, because when you have a bulky ligand, the anomeric effect loses. When you have no ligand, the anomeric effect wins. And you can use this reaction to make dozens of polypropionate natural products. For example, the cis diol can be used to make all these natural products in a fraction of the number of steps that were used before. There's no dibol, there's no swern, there's no vidig, there's no tin, there's no titanium, there's no aldol, there's no mukayama. You can tell a biochemist to make these compounds, and they, as you know, they don't know how to do organic synthesis. But now they can make it. The same thing with the trans. The trans can be used as an aldol surrogate, and you can couple once, twice, 3 times in a row, and now dramatically truncate the route to all of these natural products. Here's a deep dive into one of them. Interesting little natural product that previously took 12 steps to make. You look what they do. They need the Keck alylation with tin. They do an oxymical. You need to know a lot of organic chemistry to make this molecule. Pretty complicated, right? Alternatively, I can just take Lipitor side chain. I can do a doubly decarboxylative coupling with octanoic acid. And then I can do a doubly decarboxylative coupling with itself. I went in 2 steps to now a tetraol. That's enantiomerically and diastereomerically pure. Then there's no dibol, there's no swern. Hydrolyze, do an electrocatalytic reductive coupling with silver, and then work it up with vinegar and I get the exact same natural product. And during this process, I didn't need to know stereochemistry. So you can be ignorant and make pretty complicated natural products if you want. We can use this again to make some really valuable compounds for medchem, such as amino alcohols with either regioisomeric outcome by simply using a cheap serine-derived cassette. So in this series of 2 papers, one of which already came out a few months ago in JAX, one of which will come out soon in Nature Chemistry, we can take these serine-derived building blocks and couple with whatever you want electrocatalytically, and then upon deprotection, you get any amino alcohol that you want. You can do coupling with arenes, but you can also do alkyl couplings, acyl couplings. In the paper, which is deposited in the archive, you can check out the litany of different reactions that are used here to make almost any kind of amino alcohol that you would want. And you can use those amino alcohols to dramatically shorten the route to these compounds. No osmium involved. A question I often get is, hey, Phil, can you do these enantioselectively? And the answer is yeah. Under certain conditions, you can. So Yang Gao found that by adding magnesium and iron to these reactions and choosing the right ligand, he could now do the equivalent of an enolate alkylation enantioselectively by doing it in a doubly decarboxylative fashion. So it can be used to fashion a number of interesting compounds, but what I'm really appealed to in this is just how quick it makes organic synthesis. Take a look. So this steroid was made in this long-winded route. 15 steps to make this compound. Look at the steps for yourself. Do you want to do any of them? Maybe the sodium hydroxide step, I'll do that. But I don't know, here, look at all, it's almost like a list of the worst reactions of organic chemistry. Look at them. And at the end, these poor people did the hydrogenation and they got a 1.5-to-1 mixture of diastereomers. Tragic. In contrast, I can do the enantioselective doubly decarboxylative coupling, in this case, diastereoselective, and get the exact same product in a fraction of the number of steps, but now I've controlled my stereocenter. Here's another example. 10 steps to make this. Nobody wants to do this chemistry. Nobody I know. But they do it because they have no choice. Now, you can make the exact same compound in a fraction of the number of steps, 3 instead of 10, and get the exact same outcome. Here's another one. 12 steps to make this simple building block. How do you get up in the morning and motivate yourself to do this? Alternatively, just 2 steps from commercial, dump and stir, couple, and a fraction of the steps, I get the exact same product. So you can, choose to keep doing this chemistry, polar chemistry if you want, or you can save yourself time and then maybe take an extra long vacation with the time you saved. So if you go back to 1950, do you know what the most exciting reaction was in 1950? It was amide bond formation. And now, fast forward 70 years, do you know what the most boring reaction on the planet is? It's amide bond formation. So the question is, in the year 2070, will decarboxylative coupling be as boring as amide bond formation? I don't know. That's the hope. We like to invent boring reactions. So let me get to something that's unpublished, soon will be published, which is this vexing question that the pharmaceutical community has, which is how do we make our flat molecules have more shape? They call it departing the flatland. It's very easy for me to teach every year in heterocycles class the flatland. And this is why it's used so often, because it's very easy to conceptualize. Oh, I take a pyridine, I do electrophilic aromatic substitution, or I do a borylation, or I do a CH activation, and then I get my product after cross-coupling. Very easy to understand. And that's why medicinal chemists love to do flatland chemistry. But when they want to, let's say, endow their compound with more bioactivity, better efficacy, better solubility, they need to go 3-dimensional. But there is no general logic to do that. So when I teach my heterocycles class and I start teaching about saturated heterocycles, every time there's a new saturated heterocycle, you need to take a different retrosynthetic approach. There's no general strategy I'm aware of for making these. And certainly you can't take a pyridine like this and magically throw X groups on there and then magically do cross-couplings. That doesn't exist. But maybe it does. So we thought, what if you could combine biocatalysis and radical cross-coupling? Would it allow for a game-changing way of making 3-dimensional molecules? The saturated analog of pyridine is pyridine. How do we make these in the same way that we make boring, flat pyridine? Well, this study was done in collaboration with Hans Renata at Rice. And Jian, very, very talented postdoc, teamed up with Kawa in the lab. And Kenta was in Hans' lab. And so we took their biocatalysis, which operates in a scalable fashion, to site and regio-specifically and stereoselectively introduce hydroxyls all over a pyridine to make the building blocks in the box, which are prohibitively expensive, but now can be made through biocatalysis, which is very, very cheap and scalable. Can we take those compounds and use them in sequential radical cross-couplings to make pyridines? That's the question. So here's an example. These two compounds are medicinally important compounds. How are they made? Well, they're made using the boring chemistry we all know, love, maybe hate. Take a look. Look at it yourself. Lithium chemistry, pyrophoric stuff, reductions, reoxidations, Grignards. And at the end of the long crusade, they get their product. Yay. Alternatively, we can just take piperacolic acid, which is free. You can do Hans chemistry to biocatalytically install a hydroxyl group. And then decarboxylative coupling gives you the exact product you need in a fraction of the number of steps. How about this compound, a natural product that's been made no less than 20 times? And what I'm showing on the bottom here is the shortest route, 6 steps to make this compound. But look at the first step, some enamine thing that requires 19 days. I don't know, in Hong Kong, do they let students go away for 19 days? It's best for Europe. This is a good reaction in Europe, because I think you're allowed to take vacation there. So this would be unusable in Hong Kong, right? Alternatively, we just take the exact same intermediate, we do a decarboxylative alkylation, an Appel reaction, close it up, and you're done. So it's amenable for Hong Kong, where people work hard, versus the other approach, which you wait forever to make your compound. How about this compound, natural product? Look at how it's been made. Made a few times. This is the best way. You're doing Claisen reactions, you're doing reductions, they're not diastereoselective, chiral auxiliaries, and you get out your desired product. Alternatively, you just take Hans chemistry, different enzyme, hydroxylate, and then couple, and you're done. Super easy. How about this compound? Another medicinally important compound. How has it been made before? Using chemistry we knew from the 1980s. Kohlmann's chemistry. You take a pyridinium salt, you dearomatize it, you conjugate addition, then you need to separate the diastereomers, then you need to separate the enantiomers, and you finally get your product. Miserable. Alternatively, the same building block, do a decarboxylative arylation, and then alkylate the oxygen, and you're done. Take a look at this one. 8 steps to make this compound. How did they do it? Look at it. It's all polar chemistry. They do a conjugate addition. They do a resolution from 1960. LAH, Swern, Wittig, all the chemistry you hate. Alternatively, Hans took his catalyst, did a hydroxylation. First, a doubly decarboxylative cross-coupling to install one side chain. And then in one pot, we can do a deoxygenative coupling using Gong's reagent to give you the corresponding brominated derivative. And then in the same pot, just electrocatalytically couple it to give you the desired product directly in a fraction of the number of steps. This is my favorite one, because this one was done by Merck Process, which is arguably the most premier process group on the planet. They made kilograms of this compound using the strategy I'm about to illustrate to you by coupling these two building blocks together. I'm going to show you today a very different approach, which instead takes an iodopyridone and couples it not to the bromide, but instead to the alcohol. Let's see how that works. Let's take the first building block, one by one. They take this bromobenzoic acid. They do what I showed you before. They make a Sonogashira reaction to make an alkyne that they then need to reduce to get their product. They use platinum because they don't want to lose the bromide. So here, palladium and platinum to make a very simple compound. Alternatively, we just start with dibromobenzoic acid. We do a decarboxylative arylation, works in high yield. It gives you the desired product without touching the other bromide. And then just borane reduction of the amide down to the amine. And we have one building block in 3 steps, no precious metals at all. It's just nickel. Take a look at the other piece. The other piece is amazing. Look at this. 4 transition metals. We got palladium, 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 ruthenium, resolution, epimerization, kilogram scale. These are the best chemists in the world. Alternatively, we take Hans chemistry, we hydroxylate, we make the amide bond, and then a deoxygenative coupling with the iodo-pyridone doesn't touch the arobromide, it only touches the alcohol. It's kind of magical. And if you do the calculation, for every kilogram that you're using, that you're trying to make of this compound, you're saving thousands of dollars in all the precious metals that were used before, and now you're just using nickel, which is, basically free. So the attractive part of this approach is that it is kind of appealing from the vantage point of a medicinal chemist because you can make these compounds rapidly and modularly, and it's also appealing from the process chemist perspective because you've reduced the step count and you don't need the platinum and the ruthenium and the palladium any longer. Okay, so in the final 15 minutes or so, I'd like to turn to something very different. What is special about electrochemistry? What is something you can do with electrochemistry that you can't do with anything else? Let's talk about waveforms. When you put a battery in your flashlight, or when you drive your Tesla, it has direct current, simple batteries at the bottom that then use an alternating current motor. When you plug your hairdryer, something I don't need to do, when you plug your hairdryer into the wall, you use alternating current. That is, the waveform is sinusoidal. It delivers the current with a sine wave, whereas direct current delivers it with a flat, constant current. So I wondered many years ago, a decade ago, I started asking people that were like battery chemists. I said, how come they don't do electrochemistry with alternating current? And they said, oh, Phil, it doesn't work. People tried, and it led to mixtures of compounds. It was a mess. Don't do it. And as usual, we didn't pay any attention to them. And so the key person behind this who took a risk was my colleague Yu Kawamata, who imagined that maybe we could try to do something that was useful by changing the waveform. Now, people over the years have started to look at this. So the first two reactions are reactions we invented many years ago, an amination, sulfonate addition electrochemically, and they found that by using different waveforms, they could get different yield, slightly better yield. But you probably have noticed this already, I'm not a yield chemist. Like 50% is fine, 90%, whatever. I don't care about yield, I care about new reactivity. So I wasn't really interested in taking known reactivity concepts and making them just slightly more efficient. I wanted to find something that was just totally new. So we invented, on the Electrosyn device, a waveform called rapid alternating polarity. So rapid alternating polarity takes the cathode, where reduction happens, and the anode, where oxidation happens, and flips them faster than you can blink an eye. It flips them. And we wondered, would you get any interesting reactivity from this? And many years ago, there's, I think, thousands of these electrosyns all over the world. We updated the software with the ability to do alternating polarity. There was no paper published, and we had no idea what we would do with it. And people who owned the device didn't really know why this thing was there. But we gave it to people because, very simply, we didn't want people to buy an oscilloscope and a signal transducer to do rapid alternating polarity. If it's not democratized so that everybody at Pfizer, Novartis, or Merck, whatever, can do it, no one's going to do it. So we installed this functionality, and then we asked the question, now what can we do with it? So the idea was, let's imagine you have two electrochemical redox reactions. One of them is very slow, and one of them is very fast. What if rapid alternating polarity can reduce the slow reaction and promote the fast reaction? And we took as an example the bottom compound as a model that has multiple sites that can be oxidized and reduced. And we asked the question, a very simple curiosity-driven question, what happens? And here's what happens. So you take this imide and you expose it to standard DC electrolysis. That's the NMR, misery. Many peaks, show no oxidations, diastereomers. It's a mess of misery. Now, all we did in this reaction is change the waveform, nothing else. Look at the NMR. Clean, new compound, only B. Only B, just by changing the waveform. We didn't change the reagents, we didn't change the vessel, we didn't change the solvent. I promise you, we didn't change anything, just the waveform. And we got a completely different reactivity. And we could not recreate this reactivity chemically or in a divided cell or any means we tried. And this got us extremely excited. The scope of this reaction is really broad, so you can take phthalamides and reduce them to imides chemoselectively in the presence of a number of functional groups that you would expect could be torn up to pieces, but they're not. You can also reduce other functional groups. But what got me really excited was when HKUST showed me this result. This result still, I look at it, it's like looking at the stars at night, feeling a sense of wonder. Look at this reaction. This is insane. If I told anybody to predict the product, nobody would predict the product 18A. Everybody would predict the product 18B. How do you reduce a phthalimide in the presence of an aldehyde? That's crazy. So the level of chemoselectivity we were seeing made us realize we have something really, really cool here. And you can use this coolness to do something useful. So here's an example from Bristol Myers Squibb, where they needed to make this aldehyde number 37. And in order to do that, they needed to use all polar bond disconnections. Alylation, oxidation, protection, blah, blah, blah. Instead, we could just do an enantioselective Michael reaction, followed by a chemoselective reduction of the Evans auxiliary to give you the exact same aldehyde, which didn't see any erosion of EE. So they use this on process scale. It's very scalable. You can use this to make PROTACs, which are now the emerging field of drug discovery. Almost every company on the planet is working on compounds like this for protein degradation as a therapeutic strategy. And now you can take phthalamides and convert them into imides without going all the way back to the beginning of your synthesis. And the azide, things that are reducible, are tolerated. You can do this across a whole panel of protein degraders and then look at their activity. And the remarkable thing, these assays were done at Bristol Myers Squibb, is that the deletion of one carbonyl group can give you quite a difference in pronounced bioactivity. So you can even take this really complicated peptide containing tons of functionality, oxidizable and reducible, and look, the only thing that gets reduced in the crude NMR, the only thing we see is the compound shown on the right. It's very, very polar and difficult to isolate, so the yield is low. But in the crude NMR, it's the only thing you see, and starting material. So what's happening? Any ideas? I mean, here's a textbook. That's a textbook you learn from. The textbook tells you that this should not happen. This is your undergraduate textbook, which is now, I mean, maybe it needs an addendum to it, a footnote. So is it that phthalamides are more reactive than aldehydes? No, that's not the answer. It's a different mechanism. And so what is going on here is single electron transfer, outer sphere. So you can understand this by looking at the cyclic voltammetry, and you realize the cyclic voltammetry is correlated to the frontier molecular orbitals of your molecules. And so you can calculate the LUMO coefficient, or you can do a CV, and you realize that, wait a minute, an aldehyde is actually more difficult to reduce than a phthalimide when you do it through an outer sphere electron transfer. And that's how this chemistry is taking place. And the speed is the key to getting this type of chemoselectivity. Now, it's not limited to this boring reaction. Admittedly, it's boring. We're just doing a reduction. So let's do something more exciting than that. This is the RAP team. Kawa led it. There's Masato, who's now at Chugai, good friend of you. And they're ICA folks that worked on the software update to get that in everybody's hands, and then our friends at Bristol Myers Squibb. Now, many years ago, Pfizer came to my office. They said, hey, Phil, we want to do a Birch reduction in a kindergarten classroom. And I said, what? They said, yeah, we want to do a Birch reduction, but we don't want to use liquid ammonia, and we don't want to use lithium metal. Could you find a way to do that, like in a simple, like in a daycare center? Non-toxic, no cryogenic, nothing. And we said, okay. So we learned from Tesla. We thought, okay, what if we do the same thing that keeps those batteries from exploding? We do the same thing here. And so we added additives and invented lithium-ion electroreduction that essentially allows you to do a Birch reduction with no amines and no sodium, no lithium. You can do Birch. But the problem with this Birch chemistry, although it was used, it can be done on very large scale, is that it can't be used for things like this. It's too harsh. So if you want to reduce a thiophene to a dihydrothiophene, how do you do it? With Birch, it's very difficult to do. So take a look at this table. We took all the Birch conditions that are known, including electrochemical. None of them worked. Look, entry 5, we tried DC, less than 5% yield. All of this was just with regular waveform delivery. Now watch what happens. I'm going to take entry 5, which gives no product at all, and I'm just going to change the waveform to rapid alternating polarity, and voila, quantitative yield. Here's the NMR. Look at this NMR. The top reaction, direct current. The bottom reaction is the same reaction, but I just changed the setting on the machine. Crazy. The reaction is general, so you can do this on thiophenes, you can do it on furans, you can do it on benzothiophene, you can do it on electron neutral, electron poor aromatics, you can do it on indoles that are properly substituted. The scope is really broad, and this Birch reduction uses no metal at all. There's not even any lithium. It's just carbon electrodes and electricity. You just plug it into the wall, and you get a Birch reduction to happen. Crazy. You can use it to simplify chemistry. So these compounds before took 4 to 6 steps, and now they can be made in 1 just by doing this chemoselective Birch reduction. So how does this reaction work? The physical properties of this reaction are awesome to watch. If you do this with DC, you get bubbles. Bubbles start forming. With RAP, no bubbles. What's going on? Well, you can take this phenomenon to do something really wacky. Because proton reduction is slower than arene reduction, now I can deliberately add a Bronsted acid to my reaction. Now imagine that for a minute. If I told you, one of the students in the undergraduate lab, do the Birch reduction but add acid, it's a great way to blow up your lab and go to jail. And now I'm adding acid to a Birch reduction, and it retains the vinyl bromide. Take a look at that. You can scale this reaction up. So AbbVie actually scaled this reaction up. You can see the scale there. It's been done on now kilogram scale. Very easy to scale these reactions up. Look at the reagents. Proton source, methanol, carbon electrodes. Like, it's as close to earth, air, water, and fire as you can get. How does it take place? Well, proton reduction is super slow, but arene reduction is much faster. And because you're changing the polarity faster than you can blink an eye, you get this kind of ridiculous chemoselectivity. And at this point, it's probably worth mentioning one of my favorite animals. Do you know what this animal is? It's some sort of reptile. They call it the Jesus lizard. It really is called the Jesus lizard. Because back in the early days, when they saw this lizard, they said, this lizard is walking on water. It must be an act of divine intervention, that it could walk on water. In fact, they just didn't understand physics at the time. If you move fast, you can do magic. And that's what rapid alternating polarity is. It's not breaking any rules, it's just moving really fast. Now let's go back to Kolbe. I started this talk with the Kolbe, and I promised you I would show you this reaction. So take a look. I take that acid, I try to dimerize it with 1 olefin, 0% yield. It destroys the electrode. I try to do a Kolbe reaction with that 1 benzene ring, destroys the electrode, 0% yield. No chemoselectivity. We thought, what if we could use RAP to fix the Kolbe reaction once and for all? And so this actually works. So you can take 2 acids, and you can couple them together, and look at the reagents. Look. You can use KOH if you want instead of ammonium hydroxide. KOH, acetone, carbon electrodes, rapid alternating polarity. Now you don't need high overpotential. The chemoselectivity is super high. There's no more platinum electrodes, and it can be done on megaton scale. So take a look at some of the reagents that we can make. Some of these compounds, like look at this, $10,000 a gram, $3,000 a gram. I can make this in the auditorium in front of you. You can make these unnatural amino acids that are really expensive compounds, most of them, and now they can be made from dirt, really cheap. Now, I got into chemistry because of alchemy. Alchemy is like, you know, I think we make fun of them now, right? We say, oh, the alchemists, they were stupid. They tried to take lead and convert it into gold. What a stupid idea. Actually, they were smart. They had a great vision, a lot of aspiration. You should dream big like that. I just don't think they were dreaming big enough. Because if you go from lead to gold, it's only 20-fold increase in value. RAP allows for modern day alchemy by taking things that are free, like this $20 a kilogram, and turning it into something which is super expensive. 500,000 times increase in value, and the reagents cost you nothing. The most expensive part of this reaction is your time. This has been scaled up by AbbVie to make this unnatural amino acid, which is really useful for them in high EE. $5,000 a gram, but now it can be made basically for free. How does it work? Well, let's go back to Kolbe. If you took a pH indicator in the regular Kolbe, what's remarkable about it, it's surprising that after 100 years, nobody did this. If you look at the pH indicator, look, it's acidic. How are you going to oxidize a carboxylic acid to a radical? Carboxylic acid to a radical. How are you going to do it? It's impossible. That's why you need a huge overpotential. You need the carboxylate. And the rapid alternating polarity, take a look at the pH indicator. Now it's basic. And the carboxylate is super easy to oxidize. It's the carboxylic acid that you can't oxidize. And so the magic of rapid alternating polarity is that proton reduction doesn't happen. And that's why you have a locally homogeneous pH that is relatively basic. If you want to learn more about rapid alternating polarity, we wrote a review on it. It's been published somewhere, but the archive version is out here. And we continue to work on this interesting type of reactivity phenomenon. Taking it all the way back to total synthesis now, the electrochemistry I showed you today allowed this guy to graduate. So Brendan is now working at Gilead, and he couldn't graduate because the chemistry was not working. So he needed lithium naphthalide to reduce that tosyl group off. He needed PFA, benzene, that macrocyclization was really poor reaction. But instead, he used rapid alternating polarity to remove the tosyl. Now he didn't need any lithium naphthalide. And then the macrocyclization, which is really remarkable, he could do just using an electrochemical anodic oxidation to give you the macrocyclic ether and finish the total synthesis of dragosine. That's the advantage, I think, of doing total synthesis and methodology in the same lab. All right, so we started this work, I don't know, 14, 15 years ago, and everybody said, hey, this is a waste of your time. But I said, well, I'm academic, so I'm allowed to waste everybody's time because the federal government pays me. So we decided to work on electrochemistry anyway. We thought it might be interesting. And fast forward a decade, it seems that people care. And I think the key to getting people to embrace electrochemistry stems to three things. First, education, convincing them it's not alien reactivity. It is, in fact, ET, but not that ET. It's just electron transfer. So if you understand how arrows move, it's very easy to conceptualize how electrochemical reactions work. Next, you need equipment. When I started talking about this stuff in companies, they said, what, you want me to get a PhD in arts and crafts and get a bunch of wires and put a computer in my hood? I'm never going to do it. So we needed to work on a device that would democratize this so everybody could do it. So we teamed up with ICA, introduced the Electrosyn, and now there's thousands of these in every pharma company on the planet. This is the only patent I have that's not chemistry. It's all engineering in this patent. And then the third thing you need is enablement. Let's talk about this for a minute, because people always say electrochemistry is sustainable and it's green. But I have a little thing to tell you. Nobody in a drug discovery company cares about sustainability or your greenness. If I go to a chemist in Pfizer and I say, oh, I noticed you're oxidizing that alcohol with DMP or chromium. I have a green way of doing it with electrochemistry. They're just going to laugh at me. Say, let's get away from me. Because it's not that they don't like trees. What they really like is their job. And so if they can do something quickly, they don't care what the reagents are. But if you go to a medicinal chemist and say, hey, I noticed you're making that compound in 15 steps. I can make it in 3. They're going to say, all right, where is the device? Let me try it. It's all about enablement, folks. Giving people retrosynthetic disconnections that did not exist. Green chemistry is whatever. Let the process chemists deal with that. It's all about medicinal chemists getting to their compound faster. If you don't know anything about electrochemistry, we wrote a review that is kind of like a survival guide. So you can get up to speed very quickly. In fact, you only need about 5 or 10 minutes. If you look at this review, download it, look at the pictures. You don't need to read it. Just look at the pictures. It's enough to teach you that you can get started in doing this chemistry. And we find it to be quite addictive. So as people come to the lab, they don't know anything about eChem, and within a few weeks, it's all they want to do. If you're interested in the dichotomy between photochemistry, which is redox chemistry, and electrochemistry, which is redox chemistry, my former student Max wrote a really nice paper in accounts here you can download. And it talks about the differences, similarities, when to use one or the other. So the question I often get is, well, when do I use photochemistry? When do I use electrochemistry? Download that review. It has a really good explanation of when the two strategies are complementary and when one is better than the other. And the most important, I think I'm right on time, the most important slide of the talk is to thank these folks who made all this work possible. People like you, Nakamura, who come to our group are the people who really get stuff done, the people who are not afraid to do difficult experiments. So to them, I'm super indebted. Also to these agencies for their financial support, but most of all to the companies we work with. Because when we work with companies, they teach us what are the problems that are going to have the most rapid impact to the people who do useful things in companies. And so to them, I'm super grateful. Really grateful to the faculty for having me. It's a real honor to be here. I've enjoyed listening to all your chemistry this morning and looking forward to more meetings in the afternoon. And I'm happy to entertain any questions you may have. Thanks so much.
So thank you very much, Professor Phil Baran, for the very exciting talk. We very enjoy your chemistry. So
Thanks.
now we move on to the question and from audience. So if you have any question, you can ask. We have plenty of time today, so we can take one by one. So,
Microphone.
So any question from audience? Maybe we can start from the student first. Anyone?
Thank you very much for your talk. It was very nice.
Thanks.
I have a question about the current because for RAP, you apply only 20 milliampere. So I have a question if when you try to another current as well, like decrease or increase.
Which reaction?
I mean the RAP, the rapid.
Oh. You know, that's a variable you explore. So sometimes you do it at 2, 5, 10. So you change the current, and the other variable that we change is the frequency. So sometimes reactions work better at 30 milliseconds, sometimes 100, sometimes 60. So that's just another a variable, a dimension that you explore. For each reaction, you just check out, you know, I would say what's smart is to try 3, 5, 10 milliamp, and then try 30, 60, 100 in the frequency, and that's how you optimize.
Okay. Thank you.
It's very simple. 6 experiments will give you your optimum current and frequency. It's a great question.
Okay. Thank you so much.
Yeah.
What about the potential that you're changing each time?
We don't control the potentials. These are all galvanostatic. They're all undivided cells. So the potential is what it is.
Okay, so whatever the reaction takes place.
Exactly. We religiously avoid divided cell and potentiometric reactions, constant potential, because they're harder for the practitioner to set up. You need a reference electrode. A divided cell is misery. You need that separator in the middle, the membrane. And so, you know, our audience is not academia. Our audience is the folks in industry that have never done electrochemistry before, and they want something that's just dump, stir, press button, walk away. Yeah. Yep. Thanks.
The RAP, why you choose this way? What about the sign-shaped or asymmetrical, like electrons staying longer as a cathode instead of anode? So there's many ways of manipulating the waves.
No, yeah, it's a great point. Like why RAP versus sinusoidal? We have done all of the reactions with RAP. We tried them with sinusoidal. They don't work as well. Often they don't work at all. There's something magical about this effect of when you completely turn off current and switch it to the other side, that we get, you know, the chemoselectivity we're looking for. Now there are other groups, like there's a guy at Utah, Longlow, who does more sinusoidal waves. And there are other papers been published that some of these reactions, like our amination reaction, can be improved using a sinusoidal delivery of current. But that's, I think, if you're trying to do a fine-tuning of your yield. We have seen that sinusoidal waveforms don't deliver new reactivity. They deliver sometimes improved reactivity. So the only waveform we've tried and found something totally different is RAP. Now your other question is, how about asymmetric RAP, where you leave it on the cathode for a certain amount of time, and then that we haven't interrogated a lot simply because the software is not available for it yet. We can do it with a signal transducer, and it's something we should probably do, but in order for us to publish it, we need the software update to go on the machine. Otherwise, nobody will do it. But it's a good idea. There are probably some reactions that would benefit from, let's say, 30 milliseconds cathode, 10 milliseconds anode, and for example, that. It's a great idea. We just need to look at it. And if we find a reaction, then update the software. Yeah.
Hi, Phils. Thanks for a very nice question. And I'm a person who focuses on the electric catalysis, but not for the organic electrochemistry. So I just one remarkable thing is that you use the catalysis to shorten the procedure in photosynthesis. But however, the reagent in the photosynthesis, they have a lot of functional group. So my question is that how do you design the electrocatalysis to short for the certain procedure that you can you apply to avoid the side reaction, because that's the one remarkable thing for the electrocatalysis is that they have a lot of side reactions. And I also noticed that you mentioned the rapid alternating procedure, that you like to switch the potential between negative and positive and negative. So it's involving the oxidation and reduction. And in my opinion, they may involve a lot of side reactions. So how do you avoid this?
It's a great question. And I think it was one of the critiques at the beginning of this work was you're never going to get chemoselectivity by doing this. So in electrocatalysis, the advantage is that your potential window regime is encompassed by the electrocatalyst itself. So let's take, for example, the many reactions I showed you that are nickel catalyzed. All we need to do is have the very tiny potential window that only touches the nickel catalyst, and then it doesn't touch anything else. So the reactions I showed you today, as you recall, they all had all the functional groups of organic chemistry. We have nitro groups, we've got olefins, we've got ketones, aldehydes, esters, phenols, everything, and they're untouched. And the reason for this is because the electrocatalyst takes the brunt of the electricity. In the case of RAP, the secret there is just that the modulation is so rapid that things like Shono, a Shono reaction is a byproduct. And that happens because it spends a lot of time, the substrate spends a lot of time on the anode. So if you can reduce the time it spends on the anode, and it just goes very briefly on the anode and then back to the cathode, you can get this level of high chemoselectivity. So you can also obtain, if you look at the old electrochemistry literature, you can also obtain high chemoselectivity by doing things in a divided cell, by carefully controlling the exact potential. But the disadvantage of that is you can't do high throughput divided cell chemistry, number one, and the procedure for setting those up is too laborious for anybody in a company to want to do it. So the advantage we have is we do everything in an undivided cell, and the catalyst bears the brunt of all the injection of electrons, and it protects the functional groups from being destroyed. Now, if you take some of these reactions and you leave them for an extended period of time, then exactly what you said happens. Because you're under galvanostatic control, as you keep going, the oxidation gets stronger and stronger and stronger, and then you start destroying everything. So the key is inject only the Faradays per mole that you need, and then stop.
Okay, thanks.
Yeah.
Inspiring talk.
Thanks.
Sorry, I'm kind of towards the end of my career. Otherwise, I'd be very excited to jump into this type of synthesis. So a few things. Starting with the Kolbe reaction, I'd heard of it, but I must admit I don't remember it being taught in UG lectures to me. Apart from Kolbe, which is very beautiful that you start with 2 carboxylic acids and you can lose CO2s, and then you showed other reactions where you could have CO2H on one side and iodo on the other. Are there any other simple substrates that might lose gas? Or in the case of the halogens, does it have to be iodine? If bromo compounds would not work and so forth?
Yeah,
Any
these are
comment?
Awesome questions. So with regards to the decarboxyl arylation, we can use aryl bromides or aryl iodides. And if aryl chloride is super reactive towards oxidative addition on the nickel, so highly activated aryl chlorides will work just fine. In the case of the alkyl series, you can use iodides, or I showed one example in the piperidine of a bromide made in situ. There are other things you can do. For example, people have taken alcohols, they have made oxalate esters, and those oxalates will lose CO2 and CO and then liberate a radical. And in more recent work that we were going to deposit in the archive next month, there are ways of doing this without any redox at all. So you should begin thinking about, all of you think about what functional group would you use to liberate something, X, that wouldn't require any injection or removal of an electron. We chose acids because they're the most ubiquitous building block. Now, if you count how many alcohols there are that are available from Aldrich, there are many, but they're not often the useful ones. They're often found in natural products, and so the number is high, but the utility is low. If you count the acids, man, last time we checked, there's like 20,000 different acid building blocks you can buy. So we focused on that first because it's more like the Lego approach. You can get almost any acid you want and throw them together. So we think acids, halides derived from alcohols, are probably going to be the mainstay for the sort of redox active component that donates and then goes into an arene or an alkyl halide. But there's other ones that we'll reveal later. In fact, we published many years ago things like redox active sulfones, and people have taken amines and made Katritsky salts, pyridiniums, that are redox active as well. So whatever you can draw on paper that you can imagine, you can inject an electron or you can remove an electron, and that resulting radical would lead to an emulation event giving you an alkyl radical, can probably be employed in this chemistry.
Thank you for that. One other thing intrigued me. I know there's a lot of people working on trying to make quaternary centers.
Yeah.
And the ones that you made are awesome. But I noticed that usually there's some kind of ring. They don't seem to be chiral centers. Have you tried making chiral ones? And there'll be a way to have some stereo control there.
Yeah, that's a phenomenal idea, and the closest we've ever gotten to an anti-selective decarboxylative coupling is the one examples I showed you there on the making those secondary sites. Getting a quaternary center in an anti-selective way, that's going to be challenging. We're trying, but the problem with it, let's take a step back. Let's look at asymmetric hydrogenation. That's the go-to way that people in industry use to make chiral centers. And the reason is because there's only a handful of olefins, right? Think about olefins. There's only a few types, mono, di, tri, tetra, and some various little substituents. And so one class of ligands, if you have 200 ligands, it's enough to get a hit. Now, let's go to sp3. sp3 is crazy because you're no longer in the flatland. Every radical you generate, every cross-coupling partner is going to require a different ligand class. So I think it's a tractable problem, but I think what's going to happen in the years to come when people eventually solve this is you're going to have one ligand for each type of substrate. I don't think there's going to be a binap for making quat centers through this type of chemistry. But it's a great, I mean, that's where the field is heading. That would be amazing if you could do that. It's definitely something we want to do, and it comes down to ligand screening. Yeah.
Thank you, Phil.
Okay, any question? Okay.
Mike is here. Okay, so I'll go ahead first. Thank you, Phil, for the nice talk. I learned a lot. I consider myself more of an electrochemist. I work with Hugh and others in the department to learn from them the organic chemistry. Cool. And a lot of time I feel like our languages are a bit different. So when I see your method of rep, I was kind of interpreting in my own way, but I'm just gonna speak it out for you to correct me. So when I see it, I thought it's probably less about the rate of the electrochemical reaction, but rather about the chemical reversibility. For the case of, for example, the hydrogen generation, right?
You're right.
I mean, reverse it, you oxidize it back.
Yes.
And there's no, I mean, in an ideal case, there's no reaction following up to convert it to the next compound. But for your desired chemical reaction, it's not that chemical reversible, meaning that when you reverse it, it don't get oxidized to something else. So it's more about the I mean, it's still about rate, but it's about the rate of the chemical reaction that follows the step of electrochemical reaction. Is that a correct interpretation?
I think you're right, and it's nuanced because as part of the NSF Center for Synthetic Organic Electrochemistry, there are a bunch of computational chemists in there too, and they've studied RAP. And the RAP-Birch reaction that I showed, their calculations showed that the rate of absorption of the arene onto the electrode is fast and it stays there longer, whereas the protons don't stay there their rate of absorption is much slower. So it could be a rate of chemical process. It could also be a rate of how much residence time does the substrate have on the bilayer of the electrode before it can transfer its electrons. So I think you're right, and I think there's also a surface phenomenon taking place. So it's that center is studying, I think they have like 3 publications that they're going to be publishing just on trying to understand RAP in these different scenarios. I think each of these reactions may be a little bit different, but you're right. It's the rate of reversibility, it's the rate of absorption, it's the rate of the chemical processes. It's like a conglomerate of rates. Yeah, 100% right.
Thank you.
Okay, any question? All right.
Thank you for the talk. I have 2 questions for you.
Sure.
So, does the AC you apply differ to different? Sorry, I rephrase my question. So, does the parameter of the AC you apply differ in different functional groups you're doing as a reaction? And the second question would be, have you tried changing the frequency within a reaction?
So I didn't quite get the first question, but the second question, is it that you mean we start with one frequency and then change to another?
Yes, yes.
We never do that.
Okay.
But what was the first question?
So does the parameter of the AC change according to which functional groups you're using for the reaction?
Oh, yeah. So as I mentioned to the other individual who asked the question related to that, we don't understand, based on first principles, what functional group or what reaction would benefit from what frequency. It's all empirical. So when we screen, it's very easy on the device to tell the device, oh, I want 30 millisecond, I want 60, I want 55, I want 100. So we just do a range, 3 reactions. Usually we just do 30, 50, 100. And then we see which is best, and then we can fine tune in between. But currently, we do not have an understanding that is high level enough to be like, oh, we want to reduce that. We've never done it before. You got to use 65 millisecond. Have no idea. So at this point, it's empirical. But it's kind of easy empirical. It's like changing your solvent in a regular reaction. You just change the frequency and see what the result is. Yeah, it's a good question.
Okay, any question? We still have time, so we can take some question. Okay.
I thought there might be a few more. It's very beautiful, the work that you showed with nickel and the low cost of nickel versus many of the traditional expensive metals, the wonderful catalysis of Bob Grubbs and others. But presumably, you're not just limited to nickel, and there's lots of other cheap metals. Any other things you might want to tell people, the value of? I think you used iron, if I recall, and any other cheap metals that also offer very exciting electrochemistry?
Aside from, well, we have a whole series of papers where we've done the Nozaki-Hiyama-Kishi reaction. That is a chromium nickel-based process, but very different, and we've been able to facilitate that reaction electrochemically, and you don't need stoichiometric chromium anymore to do that. So the electrochemistry is able to recycle the chromium for you. Aside from iron, which Yu's group has done, there are some papers out there with copper. Copper is challenging because it likes to plate itself, but if you have the right ligand on the copper, it can serve as a useful mediator. There's been some interesting papers on cobalt as well. Our lab is, at the moment, looking at mostly nickel because we know how to control it. We know what ligands will do what generally. Industry has no problem using the nickel. And we're focusing a lot of effort on cross-coupling, which is what I think is the workhorse reaction of all of medchem. They want to take two building blocks and put them together. But I think iron, cobalt, copper are, there's even people who are using palladium, right? That's some of the first electrocatalytic transition metal catalyzed reactions where, people were looking at palladium. And there's some advantages there that people have observed from, there's a guy at SIOC, Tiancheng Mei, who's doing that. But I think it's kind of limitless. Like I think once people start looking at this, the number of papers that, when we started doing eChem, basically there were just some sporadic, Shono and a few other random cation pool. Nobody did any of it. And now it's kind of exploding. So it's like every day I'm seeing papers that are like, oh, that's crazy, you can do that. So I suspect in the future there'll be, almost every metal you can imagine, as long as there's an argument to be made for the redox. Like, I think most carbon-carbon bond forming reactions require some sort of redox, but not all. Most of them do. And I think for all the reactions that require redox, certainly any transition metal where there's a redox cycle, you can imagine electrochemistry could facilitate it. And there's some inherent advantages to doing it through the electrochemical means versus other ways, just because from the standpoint of simplicity, it's kind of like the asymptote. Like if you think about it, it doesn't get any simpler than just plugging something into a wall. And it's infinitely scalable. So, I think, I saw a talk by Merck at the ACS meeting about a year and a half ago where they had a very complicated photochemical process. They just converted it to electrochemistry on large scale, and that was the way to go. So I think a lot of people will gravitate towards it eventually just because it's super cheap. And as part of that, they're probably going to be looking at other metals they can use as well. But right now, most of the stuff we're doing, nickel. Yeah. Great question.
So any question from audience? So now we receive probably many questions from audience. So thank you very much for Phil for a very exciting talk. We really enjoy your talk. So now please join me to thank to Professor BARAN.
Thanks everyone.